Recording in
Hello,
progress.
everybody. Welcome back to our continuing conversation about colligative properties of solutions. Thus far, we have discussed Raoult's law and the concept of vapor pressure lowering and how that relates to an ideal solution. We've also made connections between the boiling point of a solution and its vapor pressure, which allowed us to discuss the colligative property boiling point elevation. And now we are going to look at almost the inverse of boiling point elevation, which is something we've explored in lab already, known as freezing point depression. So let's hop into it. So freezing point depression, let's get a formal definition, and then we'll explain why it is that this particular property happens when you add solute to pure solvent. So define freezing point depression. So this has a very similar definition to what we've seen in our boiling point elevation and even in our Raoult's law, the idea that maybe a change in concentration affects some kind of proportional change in solution property. In this case, that solution property is the freezing point. So we can say that by definition, freezing point depression is the phenomena where the addition of a solute to a pure solvent affects a proportional lowering in the freezing point of solution compared to the freezing point of pure solvent. In other words, the freezing point of solution will be less than the freezing point of pure solvent. So why does this happen? It's the exact same explanation as we've seen when talking about boiling point elevation and vapor pressure lowering. So let's look here, an example of water, our pure solvent. We've added some non-volatile solute, that would be our sodium chloride, here represented as little boxes. This is our salt. So let's think about what's happening when a substance is trying to freeze. So when a substance is freezing, right, you are lowering its temperature. So you're depriving the system of thermal energy, meaning you're depriving your molecules of kinetic energy, right? So pumping thermal energy out results in a slowing of molecules in solution. And for a pure substance, those molecules slow just enough to the point where the intermolecular forces that exist between those solvent particles allows for there to be this locking into place of this like macro crystalline structure, especially for ionic substances, that we see and call the solid phase. So this idea of slowing down to the point where our intermolecular forces kind of click us into place. So thinking about a solution, so an impure substance, if we're looking at our water molecules here, in order for them to be able to find one another amidst this kind of crowd of salt solute particles, we have to get these water molecules to move even more slowly so that they can then encounter one another and have these solvent-solvent interactions overwhelm and allow those molecules to, again, kind of click into place into their solid form or freeze. So the presence of the salt is, again, like another physical blockage. So we have to bring solutions to a lower temperature to allow our solvent molecules to freeze within W/In. the solution. So this is how, well, I guess we'll talk about that. I was going to say this is how antifreeze works, but we did that, right? We made that in lab. When we looked at our solution of ethylene glycol in water, you notice that that froze at a sub-zero temperature. When you made your solution of rock salt in water, you also notice that that froze at a sub-zero temperature. In fact, we were able to get that bath down to like -10 without it even freezing. So yeah, freezing point depression, interesting. Now, what does this mean for us in terms of like the actual math? Like, how do we quantify this proportionality? So the proportionality is the exact same structurally, mathematically, as we saw with our boiling point elevation. So what our equation would look like for freezing point depression would say that the change in the freezing point is equal to the negative of the freezing constant of your solute times the Van Hoff factor of your solute times the molality of your solute. So let's again go over those pieces. So delta TF, this is our change in freezing point, meaning this is looking at the difference that our freezing point of our solution has compared to the initial freezing point or the freezing point of our pure solvent. Negative K, so again, K is another solvent-specific constant. In this case, it is called the freezing constant. So freezing constant, solvent-specific. And since we are looking at water most of the time when talking about solutions, at least in Gen Chem, we use the freezing constant of 8.16 degrees C per molal. So just like our boiling constant was 0.51 something, remember I kept calling it 0.519, but I know it's not that. We have about a little over double that and a little over triple that for our freezing constant. So if we were looking at something else that wasn't water, we would have a different freezing constant. Okay, I, again, is our Van Hoff factor. This basically is something we include for our electrolytic or ionic or fully dissociable, fully split apartable solutes. Because again, all of our colligative properties are entirely dependent on how many solute particles are in the way. So if we're thinking about sodium chloride here, like each of these particles would be an Na plus and a Cl minus that our water has to navigate around, meaning that our Van Hoff factor is 2. Which lastly leaves us with our most beloved. I hope you can hear the sarcasm in my voice. Now, molality is fine, but it's not my particular favorite unit because I'm a chemist and I like molarity. So molality, this is our concentration of solute in moles per kilogram solvent. So this is our freezing point depression, FPD. Equation. And how is this a directly proportional relationship? So K is a constant, I is a constant, where K is a specific constant for the solvent, I is a specific constant for the solute. So what we see is that the change in our temperature is equal to a constant times our molality, or Y is equal to M times X, which is a linear proportion or a direct proportion, right? So this is our freezing point depression equation. why on earth do you, as students enrolled in Chem 220, care about freezing point depression? So I'm going to zoom in a little bit because I know that this is a small image. So the first example is making old school ice cream. Ice cream is not as modern as you might think it is, right? So if you were to go back and ask yourself, how is it that people were making ice cream before modern refrigeration or freezing technologies existed? It's because they were utilizing freezing point depression. So you can go to the store and buy what's called ice cream salt or rock salt, which is what we used in lab. And you can do like what this little recipe here is saying, where you can create a solution of rock salt and ice. This will allow you to get a freezing point of solution that is less than the freezing point of water. And it can even be like significantly less than the freezing point of water, because think about what ice cream is. It's just a frozen custard. So if you were to make a custard, right, that is probably going to have a lower freezing point than water, just because, again, that's a solution in and of its own right. And it's got a bunch of like milk proteins and sugar and vanilla flavorants, etc. So we can use the mixture of rock salt and ice in order to create super, super, super cold conditions. And if you were to get your custard and nestle it inside of this super, super cold bath, then you would be able to shake to ensure that every particle had that cold environment, and then make your own ice cream. So kind of fun. If you want to try this, have fun. If you're lactose intolerant, I'm sorry, but this explains kind of some cool history, right? If you were wealthy enough back in the day to afford to have ice shipped to you via some kind of freight train, then you could have ice cream made in like 1850, which is kind of wild. Another example that we have talked about briefly in lab, I think I asked you about this in your post lab, is the idea of salting icy roads. Now, I know that us Bay Area folk probably don't encounter snow, knock on wood, right? That often. But if you were to like go up to Tahoe or anywhere up in the Sierras where it does happen to snow sometimes, what you'll notice is that in addition to just plowing the roads, right, trying to clear off any fresh dropped snow or ice, to prevent any black ice or in general just ice from forming on the roads, these trucks will plow and then deposit a layer of salt, some kind of ionic salt, probably rock salt because that's cheap and readily available, onto the roadbed. And the reason for doing so is by doing that, right, by adding now our solutes, the ice, to our ice, our pure solvent, we are creating a solution, just like we did in our example of making old school ice cream, that has a lower freezing point than that of pure water, meaning we've now created a solution all over these roads that will not freeze at 32 degrees Fahrenheit. You'd have to be at an even colder temperatures in order to freeze. So this is like a safety issue, right? You salt your roads. That adds maybe a little bit of traction if you're adding an excess of salt. But the primary means or reason why we do this is so that we can get a solution on the roadbed that has to exist in a much more cold environment than maybe the environment outside that's causing the snowfall in order for ice to form on the road. So it's a safety measure. And then I know we have a couple of animal science or veterinarians in the class. So I did want to bring up another kind of interesting biological perspective as to why freezing point depression is something that's interesting and something that's kind of cool that you can calculate from a really simple little direct proportionality. So if you look at all these fish species, these are species of fish that exist in Arctic conditions. Some of them exist under ice sheets in frozen freshwater lakes. Some of them exist in saltwater, right? And the question for biologists is, how on earth do these fish survive in these really, really, really cold waters when we're like at temperatures where we expect the blood of these animals to freeze? Like, how is it that these are not, fish popsicles? And the answer is these fish have adapted over time to contain what we call antifreeze glycoproteins. So I'm going to zoom out. So there's a bunch of different variants of these antifreeze glycoproteins. They are found in relatively high concentrations in Arctic fish, and different species of fish. I almost said genus. I'm not a biologist. I'm sorry. Different species of fish will have different structural forms of this antifreeze glycoprotein, depending on whatever was easy for them to adapt into creating, right? And depending on also their environment, because we can think about size as being a means of preventing freezing. We can think about shape and surface area as a means of preventing freezing, because again, freezing point depression is all about solute molecules getting in the way physically of our solvent molecules. So here's a bunch of really funny looking fish species. I am a particular fan of, let's see here. I mean, the depiction of this one's just hilarious, right? Like, what are you looking at? But I think these eels are really cool, right? Because they've got like a really weird type 3 antifreeze protein. So yeah, if you want to go to your organismal biology professor and ask about these fish, I highly suggest you do so. Because again, the reason that they're able to survive in the environments they live in is because of this chemical property, this chemical phenomenon, this colligative property known as freezing point depression. So in our next video, now that we have a sense of like what freezing point depression is, how it happens, the calculation that we could use or the equation we could apply to figure out how depressed the freezing point is based on a particular concentration of solutes, and also generally like why this stuff is kind of cool. We're going to practice some of that math that was seen in the equation here, just to ensure that we're super comfortable with navigating all of these new variables that we've seen. So see you in our next video. We'll practice calculating the freezing point depression of a particular solution.